Alright, so in this video we're going to cover chapter 16 examples from the Nolan and Heinzen, the 6-step procedure, which is regression. So we're going to do both a simple regression and a multiple regression to kind of cover what happens when you have one predictor versus multiple predictors. So we use the same data set I used for the chapter 15 examples. So I'm going to reload my judgments of learning data. And so we have a ton of different observations, and we're looking at their score on their exam. That's going to be our dependent variable. So their score on the question on the exam, the rating that they gave that score, so how well they thought they would do on the exam. We have their previous GPA, which exam it was across the semester, so students' scores either tend to go up or down across the semester. And we have a couple of different metacognitive skills. So let's start with a very simple regression. So we'll start with our assumptions here. What we're going to do is predict their score on the exam or an item with the rating that they gave it. So can they predict how well they think they're going to do? And so the first assumption is that the IV and the DVs, which we can call them IV and DV in this case because we're picking a side. We can call it also X and Y, are at least scale variables. Well, score is ratio, the way we have, so people could get partial credit. It's not 0 or 1, so it is a ratio variable. And then the rating variable is also ratio because they rated it from 0 to 100. And now we need to know that X and Y are normal. Well, in this case, we have 3,700 observations, so we've hit the central limit theorem where n is greater than 30, so we can assume that it's normal. When we have random selection, well, if I consider this, again, to be just my class, I could say yes, but if I consider this anybody who's taking a statistics course, I could say no. And random assignment is also no, because I can't randomly assign which exam it is or what score they're going to make, that sort of thing. Let's make a plot for homoscedasticity. Since this is simple regression, we can do the plot first. Okay. For multiple regression, we tend to do that plot at the end because it's just easier to make the plot once you're done. Alright, so I'm going to load ggplot, I'm going to load my theme so I get a cute plot. Remember here that the first thing after ggplot is the name of the data set, so I'm going to call that JOL data. And we're looking specifically at score and rating. So rating is my X variable, I'm going to put that in the first spot. Score is my Y variable, I'm going to stick it in the second spot. It doesn't matter so much on simple regression, but it will matter once you get into multiple regression. Let's see, we want to call the X label here rating, and the Y label here score. It warned me it's deleted some missing data, that's okay. And I would say that this plot actually looks pretty good. Now, I don't know how much of a correlation I'm going to have, but the spread is relatively even. Now, there are more dots bunched up over here, so you could say no, because there are more dots bunched up on the right side here. And that's mostly because I teach honors classes, so we don't tend to have people who rate themselves very low and then these scores very low, but I would say it looks relatively even. Okay. You could also tell me that you think that these are too bunched up over here, and I would give you credit for that. Okay. Step 2 here would be to write out the research and the null hypothesis. So our research hypothesis here is that their rating predicts scores, or that B is not equal to 0. Okay. The null would be that the rating does not predict scores, or that B is equal to 0. Okay. For step 3, we're going to write out our equation. Okay. So that's where I'm going to run this code here. So I want to predict scores, y goes first, with rating. Remember that it's y is predicted by x. Data, leave this word data alone and change this word here to JOL data. And let's run that. Score is not found. Oh, because it's called score, my fault. We're just gonna take this, put it all into step 3 here, and we'll use that to write out our equation. So y equals A is this one, so 0.45. So most people are getting an average of like half the question right, plus 0.004, so it's a very small number here, but that might be due to the scale of the variable. So it's very small numbers can also be significant predictors. 0.004, and then I fill in x here. But it might even be better to just say rating, which is x. Okay. There should be a times. There it is. Okay. So remember this formula is y equals a plus b times x, right? And we're filling in a and b. Leave y and x. And it might even better here, we're actually trying to predict score. So a person's score equals 0.45 times 0.004 times rating. So what you might see is a question that says, what would someone score if they rated themselves as getting a 70? So what I would do is say score equals 0.45 plus 0.004 times 70. I'm going to make R do that for me since I am bad at calculators. And their score is 0.73. So I would expect them to get that question 3/4 right. Just an example, this is really what you need for step 3. Step 4 is to come up with a cutoff score. So I'm going to use these degrees of freedom here to come up with my cutoff score. So I've got QT, 0.05 divided by 2, 3,667, lower tail equals false. Come over here. And that's going to be what this line should be. Okay, I skipped beta, I'll come back to it. So it's 1.96 minus. Where's the minus? I have this thing on my keyboard, sometimes I can't remember which keys are where. Anyways, that's just say minus. And I'm struggle busing right now to figure out where the heck the minus is. There it is. Okay, 1.96. Okay. Another thing you might get asked for is what is the standardized predictor? Okay, I kind of skipped that. And that's where we would calculate beta. I have quant sci, so I'm not going to install the package, but then I would run lm.beta, and I would find that the standardized predictor is 0.21. All right, step 5 is figure out the t found in our study. Well, it's going to be up here. We're going to use the rating line, so here's t. It looks better when you look at it in R because it prints out like they line up, but it's 12.76. So step 6 is, do we reject? Is 12.76 bigger than 1.96? Yes, reject. Therefore, ratings predict scores. Okay. So their rating on their how well they think they're going to do actually does predict how well they did on the test. I wouldn't say their rating caused their scores, but I could say that I expect their ratings to be related to their score because I have a good idea for how well they think they're going to do. All right, let us try now a multiple regression with that same data set. So what we're going to do is pick a couple of variables here. So let's say we're going to pick score. as still as our DV. And let's see if we're going to use rating again. Other things add to the equation. So does having multiple variables make it useful? So let's look at their previous GPA, the exam time. So do their scores change across semester? And then if you watch the correlation video, you know that self-efficacy was related to their ratings, so maybe self-efficacy will be related to their scores. So their self-efficacy predict their ratings. Maybe it'll also predict what they actually made. So we'll just pick those 4 just to kind of keep it easy. Now if I think about all of these variables, are they all scale variables? Because that's the first assumption that we're going to talk about. Okay. Well, rating and score, we decided a minute ago, were ratio. GPA and self-efficacy are interval. You can't really get a 0 GPA. So yeah, all variables are scale. The second one is all variables are normal. Okay. And we've definitely got n greater than 30, so we can assume yes. Random selection and assignment, we just finished the same example, so basically no, we don't have all stats people, and I really can't randomly assign you a GPA. Or randomly assign you a score. You probably wouldn't like that very much. And then homoscedasticity, we're going to stop and come back to. And hopefully I will remember to come back to it, unlike in class. Step 2 is to come up with a prediction. So our research hypothesis is that the variables, so rating, GPA, I left a variable out a second ago, self-efficacy, exam time. Right, that's interval as well. There's no 0 exam. So rating, GPA, self-efficacy, and exam time predict scores. So this is where B is not equal to 0. The null would be that rating or GPA or self-efficacy or exam time do not predict scores. So B equals 0. And we're actually testing 4 different hypotheses here. So 1 for each predictor. We're just kind of lumping it all together into one test in one sort of written out procedure. Step 3 is to write out that equation. So let's run our multiple regression. Remember that y goes over here and all of our x's are added together. Our data set is JOL data. We're going to take this summary and we're going to do a couple of things with the summary here. Now, if you asked me what the equation was, what I'm going to do is I'm going to say your score, or y here, equals A, so that's this first one here, so negative 0.5. So the average score in this is actually less than 0, which is a little weird to think about, but that's because the other predictors in the equation are tilting it up more, because you really can't get less than 0 in this. So that is bringing that intercept down because of the other predictors. Okay. Plus rating times its slope, so it's 0.003. Okay. So 0.003 times rating plus GPA here. So 0.25 times GPA plus negative 0.03, so it's actually negative, times exam time. Okay. That's first exam, second exam, third exam, plus 0.05 times self-efficacy. Now these are all very different scales. So I have this equation, but I don't know if I would know which predictor was the best one or even how to compare them because GPA is definitely not on the same scales as this 1 to 5 rating. So let's get those beta values so I can compare them to each other. Okay. The code's L and beta, and then use output because I've already turned on the package. And so it's really tempting to just look at the numbers here and say GPA is the best. But remember that rating and GPA are very different scales. So if I look at this with some appropriate spacing so I can actually see the predictors, right? In this particular case, there we go, now everything's lined up. Rating is actually the highest. So their rating of their score is actually a bigger predictor than GPA. Now, 0.16, 0.14, they're about the same. So these two predictors are about equal. And actually these two predictors are about equal. Just one of them is negative and one of them is positive. So a negative score for exam time to me implies that as we go through the semester, scores are going down. Okay. But all the rest of these are positive. So as I rate myself as doing better on the test, I do better. If I have a higher previous GPA, I do better. As the semester goes on, and we get to that last exam, we do worse. And then self-efficacy, as I have more self-efficacy, I do better on the exam. So my scores are higher. And that kind of makes sense. I feel like I'm doing better, I have a better GPA, and I have the confidence that I'm going to do better. But that last exam is harder than the first exam. Okay. All right, so that was step 3. Step 4, remember the degrees of freedom when you have multiple predictors is a little tricky. So we're going to make sure we use the degrees of freedom from our output here. So 3664. So we're going to do QT, 0.05 divided by 2, because we're always doing two-tailed tests right now. 3664, lower tail equals false. Let's come over here and get that. So I got 1.96, I'm just so close, honestly, because it's such a big number. So I've got plus and minus 1.96. And I'm going to figure out where minus is on my keyboard, I promise. Step 5. Oh, it's the end of the semester. The word step, I can't even spell it anymore. Is we're going to use all these t values from up here. So I'm just going to kind of copy this, come down here, paste this. So for rating, our t equals here. Okay. And then for GPA, t equals this 844. For exam time, t equals this negative number. And then finally, self-efficacy, t equals this number. Step 6 would be interpretation. So for rating, is that bigger than 1.96? Yes. It's rating predicts scores. Okay. GPA also bigger than, oh, I wouldn't say yes, I would say reject. Sorry. Keep consistent here. GPA also predicts scores. The exam time also predicts scores because that negative 5.36 is bigger than 1.96. And then self-efficacy here, also reject. I picked a really good example. So self-efficacy predicts scores. They're all predictive, which is really cool. That's awesome. But now I could use beta here to figure out which one's the best. The last thing you might get asked about is effect size. So this was where you want to use multiple r squared. And multiple r squared in our example is here. You don't want to use adjusted r squared, use multiple r squared. Oops. The 0.808, this is a medium effect size. Remembering that 0.01 is small, 0.01 is small, 0.06 is medium, 0.14 is large. So it fits right there in medium effect size. So all 4 of these together only predict 8% of the variance in scores, which implies that I'm not really predicting a whole lot of why people are getting the score they're getting, but I'm predicting a significant amount of what they're getting. So practically, I think this is pretty important because it's important to understand like how students score the way they do on exams, and maybe we can work on making the last exam people do better on it. And maybe I can think about like self-efficacy. Can't do a whole lot about GPA, but it's still not a whole lot of the exam score. So that's like 92% is due to something else. So all that together is a simple and multiple linear regression using the 6-step procedures from the Nolan and Heinzen.